Let us solve some problems related to one-dimensional motion or motion in a straight line. Some basic numericals related to one-dimensional motion. So the first question is a displacement time graph of a moving object is provided. Displacement in meter has been plotted along the y-axis. Time in seconds has been plotted along the x-axis. We have to determine average velocity in the first 4 seconds. Then we have to determine the time interval after which the body again reaches the starting point. The third question is you have to find the displacement at the end of 10 seconds and the average velocity in the interval 7 to 10 seconds. So if you look at the graph, it is not a very regular geometric pattern. The first portion is trapezium and the second portion is also trapezium, but in the displacement time graph, it has been marked by several points. Point A refers to the origin. There is a point B, C, D, E, F, G and H. So if I try to relate the points with the corresponding time and the displacement, it will be of this form. So this point B, if I drop a perpendicular, it is associated with 1 second interval, and here it is 5 meter displacement. Point C is associated with 3 seconds and corresponding displacement is 10 meter. Point D is associated with time interval 5 seconds. Point F is associated with time interval 9 seconds and point G with 12 seconds, and the corresponding displacement is obviously minus 10. So this is the graph. So the first question is average velocity in the first 4 seconds. If you see the graph minutely, at the point C up to the point B, the displacement time graph is parallel to the time axis. So if the displacement time graph is parallel to the time axis, it means that the body is stationary. Its position has not changed at all. That means obviously in this interval, the velocity should be 0. But you have to calculate the average velocity. So if at the point C you can calculate the velocity, then you can definitely realize the average velocity. So at 4 seconds, the corresponding displacement is 10. At 3 seconds also it is 10, at 4 seconds it is 10, at 5 seconds also it is 10. So average velocity will be simply displacement by time. So the first part of the question, the average velocity will be obviously the corresponding displacement by the time interval. Displacement is 10 meter and the time interval is 4 seconds. So that is 10 upon 4 meter per second, which is obviously 5 by 2, that is 2.5 meter per second. The second part of the question is the time after which the starting point is achieved. If you see the graph minutely, the displacement is 0. I mean, the body has not changed its position, and so the velocity is 0. Displacement is not 0, displacement remains same as 10 meter. So from A to B, from B to C, there is a constant velocity. The slope of the graph AB and the slope of the graph BC will determine the velocity there. But the body has become stationary in this interval C to D. Then as the graph is descending downwards up to E, it means that at 6 seconds or at any instant between 5 to 7 seconds, the displacement is decreasing, which means that the body has changed its direction of motion, and so at 7 seconds it again reaches back to the same position from which it started. Similarly, in this section, the displacement is changing corresponding to the time interval but up to F to G, the displacement remains constant, which means the velocity is again 0, but again the body has changed direction of motion, and so at 13 seconds again it has come back to its starting point. So the time after which the starting point is reached is after obviously 7 seconds and 13 seconds. Now this is a graphical representation. If you consider the straight line motion, say for example the body is moving along a straight line. The body has started its journey from the point O. So up to 7 seconds, suppose it has reached here, up to 5 seconds, it has travelled up to this point, suppose up to 5 seconds. Then in the 5 to 7 interval, in the next 2 seconds, it has again come back at this position. Then it has moved to somewhere else and then again come back to its position after 13 seconds. So the starting point is achieved after 7 seconds and 13 seconds. So directly from the graph we can realize this, because if the displacement becomes 0 exactly at the given time instance, it means that the body has reached its starting point. So the time intervals after which the displacement becomes 0 again, it means that the body has moved towards its starting point. The next part is displacement from the initial position at the end of 10 seconds. Quite obvious, at the end of 10 seconds the displacement is definitely minus 10 seconds. So the third one is quite easy. From the graph directly you can say the displacement is minus 10 meter. Minus means the direction has changed. Actually, in terms of value or magnitude, the displacement is 10 meter, but as the direction of motion has changed, direction of motion is now towards the starting point, and so as the direction has reversed, it is minus 10. And average velocity in the interval 7 to 10 seconds. So from 7 to 10 seconds, at 9 seconds, you see that the displacement is not changing at all, so the velocity becomes 0. So in this interval, just if we calculate the displacement by time, you will get the average velocity. So here the average velocity will be again displacement by time. So the corresponding 7 to 10 seconds, the displacement is minus 10, and so it will be minus 10 by 4, that is minus 2.5. Here again the minus sign indicates that the direction of motion has changed. The direction of motion is now towards the starting point. Up to 7 seconds, the direction is away from the starting point, and from 7 to 13 seconds, it is again towards the starting point. That's why the velocity is negative, because it is a vector quantity. Displacement is also negative because it is a vector quantity. Negative sign for vector quantity indicates their direction. Let us look at another simple problem. The problem 2. You have to draw a graph associated with the problem. It states that a ball is moving on a smooth floor in a straight line with uniform velocity 10 meter per second for 6 seconds. At 6 seconds, the ball hits the wall and comes back along the same line to the starting point with the same speed. You have to draw the corresponding velocity time graph and find the total distance and displacement. So let me try to analyze this. So you have to calculate the velocity, you have to determine the velocity time graph. So suppose along the y-axis we plot the velocity, suppose in meter per second, and along the x-axis we are plotting the time. Obviously, time in seconds is plotted along the x-axis. So it says that the ball moves on a smooth floor in a straight line with uniform velocity 10 meter per second. Uniform velocity means the velocity is constant for 6 seconds, for the first 6 seconds. So suppose 1, 2, 3, and suppose this is 6 seconds. 3 seconds interval I am considering. First 3 seconds, then 3 seconds, 6 seconds. So up to 6 seconds the velocity is uniform, that is 10 meter per second. So that means it is moving away from the reference point, so it is plus 10 meter per second. So suppose this refers to 10 meter per second. 10 in meter per second is 10 meter per second. So the velocity is constant. So the velocity time graph will be a straight line parallel to the time axis. So up to this point, up to this interval 6 seconds, the velocity is constant. The dotted line indicates that this graph ends up to this point and the associated time interval is 6 seconds. The dotted line is not a part of the graph. It has just been shown to relate the velocity at 6 seconds. Now, you have to observe that at 6 seconds the ball hits the wall and it again comes back along the same line to the starting point. That means the direction of motion has changed. It is now opposite. So because the direction is changed, its velocity remains same, because the question says that the ball hits the wall and comes back along the same line to the starting point with the same speed. So the speed has not changed, but the direction of motion has changed. So now we have to say that the velocity is minus 10 meter per second. So because for the first 6 seconds it was 10 meter per second, obviously if it travels on a smooth floor without any obstruction, definitely it will take again further 6 seconds to come back to the same point from which it started. So the graph will be something like this for the next 6 seconds. Suppose this is 9 seconds and this is 12 seconds. Seconds I am omitting because time is already in seconds. So 3 seconds, 6 seconds, 9 seconds and 12 seconds. So after 12 seconds it will again come back to the starting point and it has reversed its journey from the 6 seconds. So from 6 to 12 it will just come back to the starting point. So now the velocity is negative, that means the direction of motion has changed. You have to say that the velocity is minus 10 meter per second. So this will be the nature of the velocity time graph. You have to find the total distance. You have to simply calculate the area of this graph and add it. So definitely distance will be now distance will be area of this rectangle plus area of this rectangle. So 10 into 6 plus 10 into 6, that is 60 plus 60, obviously 120 meter is the total distance. However, for displacement you have to consider the direction also. So in the first part this is 10 into 6 and the second part this will be minus 10 into 6, because this with sign you have to take, because displacement is a vector quantity. So if you consider the length into the breadth is in 6 seconds, 12 minus 6, that is 6, but in terms of length it is minus 10 because displacement is a vector quantity. So this will be minus 10 into 6. So obviously 60 minus 60, and that is 0. So displacement is 0. Even without calculation we can say that the displacement is 0, because the question says that the ball hits the wall and comes back along the same line to the starting point. So if the ball again comes back to the starting point, obviously its starting point and finishing point are both the same, and so the displacement is obviously 2 more problems on graph in one-dimensional motion. So the next question is, a stone is thrown vertically upward with an initial velocity of 40 meter per second. We have to draw the velocity time graph of the motion of the stone till it comes back to the ground. And in the process, we have to calculate the maximum height and the total distance covered, also the net displacement of the body. We have to assume that g is 10 meter per second square. So the first obvious answer from this question is that the displacement is 0. The displacement is definitely 0. We need not calculate it further. The displacement is obviously 0, because the stone is thrown vertically upward and it comes back on the ground. It is thrown vertically upward, it comes back on the ground. So the displacement of the stone is 0, because it comes back from the same point from where it has started its journey. So no need to calculate displacement. It is quite obvious that displacement is 0 from the question itself. The next part is we have to calculate the maximum height, the total distance, and we have to draw the velocity time graph. So if you try to analyze the motion, Initially, when the stone is thrown vertically upwards with this velocity of 40 meter per second, as it reaches its maximum height, its velocity will become 0. At the moment it reaches its maximum height, its velocity will become 0. That means for the first part of the journey, it is a uniformly retarded motion because the velocity decreases from 40 meter per second to 0 meter per second until it achieves its maximum height, and the retardation is at the rate of minus 10 meter per second square. Because in the vertically upward direction, we have to assume that g is minus 10 because acceleration due to gravity is always in the vertically downward direction. So the velocity becomes 0, and we have to then find the time after which the velocity becomes 0 because that is required in the velocity time graph. So we have to plot time and the corresponding velocities. So it is required to find the particular moment at which the velocity becomes 0. So for the first part of the journey, equation is v equal to u minus gt because it is a uniformly retarded motion. The initial velocity is u, that is 40 meter per second. The final velocity is 0 when it achieves the maximum height. So that is 40 minus 10 into t, which means that 40 equal to 10t, minus 40 is minus 10t, minus cancels out, which means t is equal to 4 seconds. So after 4 seconds, the velocity becomes 0, and after 4 seconds, the body has achieved its maximum height. So you have to find the maximum height. So then again you can use the formula h equal to ut plus half gt square. So h max of the maximum height is equal to ut minus half gt square because for the vertically upward journey it is uniformly retarded. So in place of g we will write minus g. So u means 40, time taken is 4, we have calculated, minus half into 10 into 4 square, which gives 160 minus 5 into 16, that is 160 minus 80, that is 80 meter. So the maximum height achieved is 80 meter. And the total distance covered, definitely until it reaches its maximum height, it is 80 meter, and when it comes back to the hand at the same position, again it is descending by 80 meters. So net distance is obviously, or the total distance is obviously 80 plus 80, that is 160. Total distance 80 meters vertically upward journey, 80 meters vertically downward journey. So obviously total distance is 80 plus 80, that is 160 meters. So now we have to draw the velocity time graph. So these are the calculations. You can note it down. So in order to draw the velocity time graph, let me omit this part of the solution. So initial velocity was 40 meter per second. Suppose this is velocity along the y-axis and time along the x-axis. Suppose time along the x-axis. So initially at time t equal to 0, the velocity was 40. So this is suppose 40 meter per second. After 4 seconds, it has achieved the maximum height and the velocity has become 0. So velocity becomes 0. So this will be the graph after 4 seconds. The velocity reduces to 0 at a uniform rate of minus 10 meter per second square because it is uniformly retarded motion for the vertically upward. For the vertically downward journey, g is positive, but definitely the direction of motion has changed. The particle has achieved the maximum height, now it has changed its direction of motion and it is following down. So definitely the velocity will be minus 40 meter per second when it reaches the hand. This will be a straight line, definitely. So at the same time it will take to reach the hand. So after 8 seconds it will reach the hand, come back to the hand. This is 4 seconds, and the velocity corresponding will be minus 40 because the direction of motion has changed. will be the velocity time graph. The velocity has been plotted. The velocity is in meter per second. So this will be the velocity time graph. This is a straight line totally up to this point. In the first 4 seconds, it is uniformly retarded motion. In the next 4 seconds, it is uniformly accelerated motion. In this section of the journey, g is negative. In this section of the journey, g is positive. But in this section, velocity is positive. It is vertically upward. The velocity has changed in direction. That's why it is minus 40 per second. Now you can observe that instead of calculations, just by the graph, we can find the total displacement and the total distance. So obviously, we know that the area of the velocity time graph is the distance, and with direction, if you consider it, then we can calculate the displacement also. So if you calculate the area of this portion of the graph, this shaded portion, and the area of this portion of the graph, and add it simply without considering the direction, then you will get a total distance. So area of this triangle is obviously half into base into height. Base into height, that is 40. And area of this triangle, it is half into base is 8 seconds minus 4 seconds, that is 4. Into the height is again this 40. We are ignoring the direction, that is minus 40. Instead of minus 40, we are taking plus 40 because in case of distance, we ignore the direction because it is a scalar quantity. So half into 4 into 40 is obviously 80. Again, this is 80. So if you add 80 plus 80, you will get 160 as the total distance traveled. 80 plus 80 is 160. But when you are calculating the displacement, you have to take half into 4 into minus 40, which will give you minus 80. And so 80 minus 80, the displacement will be 0. So this is another alternative way of calculating the net distance and the net displacement also. So let us move on to the second part of the question, second question in fact. So from the velocity time graph that is given in this diagram, you have to state the nature of the motion of the particle, the displacement at 6 seconds, and so on. So first we consider the nature of the motion. So if you can observe the graph minutely, in the first 4 seconds you see that the velocity is increasing at a uniform rate, and in the next 2 seconds, from 4 seconds to 6 seconds, it is decreasing at a uniform rate. So in the first 4 seconds it is uniformly accelerated. So nature of the motion for the first 4 seconds it is uniformly accelerated motion, and in the next 2 seconds it is uniformly retarded motion. Now we have to calculate displacement at 6 seconds. Obviously for displacement at 6 seconds we can calculate the area of the graph, that is displacement at 6 seconds is equal to half into base into height, area of this graph. Obviously this is a triangle, so half into base is 6 into height is obviously 2, so that is 6 meters. So 6 meters is the displacement at 6 seconds. Now it is asked to compare the distance traveled from 0 to 4 seconds and the distance traveled from 4 to 6 seconds. So again we have to find the area of the first triangle and the second triangle and compare it. That means you have to find the ratio. So the third part of the question, the ratio is area of this section plus divided by area of this section. So that is half into base is 4 into height is 2 divided by half into base is 6 minus 4, that is 2, and the height is 2. So it is obviously 4 by 2, so the ratio is 2:1. So the ratio in third part is 2:1. Now the acceleration in the first part of the journey, acceleration from 0 to 6 seconds. We know that slope of the velocity time graph is the acceleration. So acceleration in the interval 0 to 4 seconds, it is slope of the graph, that is height by base of this right angle triangle. So this is 2 divided by 4 that is half, that is 0.5 meter per second square. And for the retardation, in the next 2 seconds, it is equal to slope of this section of the graph, that is height by the base of this right angle triangle. So height by base, that is again 2 by this much, that is 6 minus 4. Obviously 2 divided by 6 minus 4, that is 2 upon 2, that is 1 meter per second is the retardation. So it's quite easy. You can easily calculate the distance traveled, the displacement, etc. from the graph. In this graph, the direction of motion has not changed, but the body has accelerated in the first 4 seconds. It has achieved a velocity of 2 meter per second, and then the velocity decreases at a uniform rate. That means there is a retardation in the next 2 seconds, and ultimately the velocity becomes 0 after 6 seconds. But the direction of motion has not changed at all. The body has started its journey, accelerated uniformly, retarded uniformly, and then its velocity has become 0. So it is a partially accelerated and partially retarded motion.